In this last chapter, we'll have a brief introduction to the application of estimation technique to navigation systems. The problems of navigation and target tracking are very closely related. Target tracking is the estimation of the state of a moving object based on remote observations of the object. Navigation is tracking of the own ship, the platform on which the sensor or sensors are located. It answers the general question, where am I, by estimating one's own state, position, velocity, attitude, and sometimes acceleration. Another problem which incorporates both of the above is the guidance problem, which is concerned with the following question: which way leads to a desired destination? It would determine an appropriate sequence of actions to reach that destination. That's called a guidance command. And this is a control problem based on the information obtained from typically a navigation system when the destination is a moving object and we have a system that tracks this object. So it's a combination of navigation, tracking, and control. Speaking of navigation, the primary considerations for the development, choice, and design of a navigation device are cost, accuracy, self-containment, security, worldwide capability, high availability, and so on. Certain navigation systems, like inertial systems, are capable of being a standalone means of navigation, mainly because they are self-contained. Other navigation devices can be used only as navigation aids to improve the navigation accuracy. Estimation and filtering techniques, especially Kalman filtering, have found extensive application in navigation because they can significantly improve their accuracy. It turns out that a lot of the errors are quite well modeled as white noise entering linear or nearly linear dynamic systems, and this is why the estimation of the state can improve the accuracy over the measurements. In this chapter, we'll have a brief introduction to the application of estimation and filtering techniques to the global positioning system, GPS, inertial navigation, and a discussion on their integration. We'll cover complementary filtering for navigation system using multiple sensors, inertial navigation system, state models, and sensor models will be also briefly discussed. And then we'll go and discuss GPS, the global positioning system, its principle, what are the observables, what are their accuracies. There are state models and measurement models that have to be used there in order to enhance the accuracy to extract the maximum information from those measurements. And we'll have a brief example of an IMM versus a Kalman filter in a navigation problem with GPS. And we'll discuss integrated navigation where there are several schemes. Complementary filtering for navigation is the relatively old technique that takes advantage of the following observation. There is a key estimation and filtering concept in complementary filtering, and it is a distinctive feature of state estimators used in navigation. The philosophy of complementary filtering is best explained in the framework of Wiener filtering, which is nothing but the frequency domain approach to the same problem as the Kalman filtering solves, except that it is done in the frequency domain, and obviously it is for stationary processes. So it results in a time invariant filter, which is the same as the steady state Kalman filter. So the Wiener filter is really a steady state Kalman filter for problems specified in the frequency domain. if we are given noisy measurements, Z is a signal plus noise. The Wiener filtering problem is how to recover the signal ST from the noisy measurement ZT optimally, in the sense that the mean square error between the recovered signal and the true signal is minimized. This is discussed in the text in section 9.5, which we didn't have the time to cover in this online course. Now, one of the fundamental assumptions of the Wiener filtering is that the signal ST is a stationary random process with known power spectral density. Using the power spectral density, which is defined only for a stationary random process of the signal and the noise, one can obtain the transfer function of an optimal filter that provides the minimum mean square error in extracting the signal from the noise. How does complementary filtering work? If we have two independent measurements of the same signal, Z1 is S plus N1, Z2 is S plus N2. Now, if the signal S can be modeled well as a random process with known spectral characteristics, Wiener filtering techniques can be used, at least in principle, to recover it optimally from the two noisy measurements Z1 and Z2. However, if the signal S of t cannot be properly modeled as a random process with known spectral characteristics, Wiener filtering techniques are not applicable. If we don't have effectively a stochastic model for the signal, then we can use a complementary filter approach as follows. And we have this shown in figure 1 coming up. There is a Z1, which is S plus N1, and Z2, that's S plus N2. And if we use a transfer function H here and 1 minus H here, the result will be that the sum of the outputs of these two will be approximately the signal. Times H times 1 minus H recovers the signal, and the hope is that H reduces significantly N1 and 1 minus H reduces significantly N2. So H is designed to remove those two noises if they have different spectral characteristics. H would attenuate N1 but let N2 pass as much as possible. Therefore, 1 minus H will attenuate N2. So with this complementary filter, H attenuates N1. It does not attenuate N2, but then 1 minus H attenuates N2, so we manage to reduce the effect of both noises and recovered the signal just by knowing the spectral characteristics of N1 and N2, which have to be different. What's also good about complementary filtering is that it satisfies an additional constraint that we have in applications. The signal is not distorted. Nevertheless, in the case where the signal can be properly modeled as a random process with known spectral characteristics, the complementary filtering is just a conservative philosophy. And in that case, compared to Wiener filtering, it will not be as good. However, if the signal-to-noise ratio in the measurements is fairly high, 20 dB at least, the performance improvement of the Wiener filtering over complementary filtering is relatively small. The problem with navigation signals is that they can be rarely modeled in a good way as random processes. We really don't know their spectral characteristics. The signal-noise cross-power spectra are not known in practice. There's a cross correlation between the signal and the noise, so there's a cross spectrum between the signal and the noise. In addition, these signals have much greater power than the noise, and thus the performance degradation in the conservative approach of complementary filtering is marginal. Complementary filters are often used in two levels in navigation. Within an inertial navigation system, the filter is used to compensate the measurement errors of this INS, and second use is for the integration of an inertial navigation system and other navigation systems. The filter can be used to estimate the estimation errors of the primary navigation system. Here's an example. The heading psi of a vehicle is to be estimated based on measurements of a flux gate compass and the directional rate or rate gyroscope, which is expressed in the Laplace domain, the frequency domain. Psi 0 is psi plus psi noise, and Rg is R plus Rn, where R of S is the derivative of psi, is the heading change rate, and psi n and Rn are the compass and gyro measurement noise respectively. So the compass, that's a psi sub c, measures the heading, and the gyro will measure the heading change rate. So what we have here is two measurements, one of the first variable and the other one of its derivative. It is known that the compass provides reliable information at low frequencies only. In other words, the spectrum of psi n, the noise in the compass, is mostly in the high frequency region. While in the same low frequency band, the gyro exhibits a bias and drift phenomenon and is therefore useful for high frequencies. Namely, the spectrum of the gyro noise, that's Rn, is mostly in the low frequency region. So we have this opportunity, one noise is high frequency, one noise is low frequency, to get rid of them in the manner that a complementary filter can do. So that's where complementary filtering is useful. We can convert those equations into the standard form by setting Z1 is the psi compass and Z2 is 1 over S of the gyro observation. So we integrate the gyro's observation and use it on top of the compass observation. So the integrated heading rate is heading, and here we have directly heading. Then we can estimate the heading using a complementary filter. So psi hat S will be, this should be a psi CS plus psi NS H. Parentheses are missing here. That's a heading, psi S plus psi N. This should be multiplied by H. Both of these are multiplied by H. And then the integrated version of the output from the gyro will be multiplied by 1 minus H. In this case, the estimation error will be the compass noise times H plus the noise from that's the gyro noise times 1 minus H. And here actually there's no need for brackets because we had the psi once as multiplied by H, once by 1 minus H. So this is the actual psi, this is correct. Psi noise, that's the compass noise, and this is the gyro noise. So the estimation error, psi tilde, has the compass noise multiplied by H, gyro noise multiplied by 1 minus H, and therefore, because Rn is significant in the low pass, psi is significant in the high frequency regions, H should be low pass. So this will attenuate the low pass noise, 1 minus H will attenuate the high pass noise, and this is going to be a reduction in the overall error. A simple filter for this case would be a constant over S plus a constant, where this gain K is a design parameter to meet a target break frequency dictated by the frequency characteristics of the compass and the gyro. Now, Kalman filtering techniques can be also used to determine the optimal K value, because complementary filter can be treated as a simple Kalman filter. So in practice, such a simple complementary filter structure is modified to meet additional constraint, such as to reject the steady-state bias of the rate gyro. So the real world is a little bit more complicated, but this shows how one can use the H and 1 minus H to get rid mostly of two noises. Now, what is an inertial navigation system? It's really a dead reckoning system, provides a non-jammable, self-contained and non-radiating, totally closed system for navigation, can be used as standalone or combined with other navigation systems. There are three basic functions in an inertial navigation system: sensing, computing, and outputting. The sensors are accelerometers or gyroscopes as gyros, which measure linear acceleration. Accelerometer measures linear acceleration, and gyroscope will measure rotational rate or angular velocity of the vehicle. And estimation and filtering techniques are used in the computation of the navigation solutions based on measurements from these sensors. What we need is really three-dimensional navigation for a vehicle with 6 degrees of freedom, 3 displacement degrees of freedom, 3 rotations. We need 3 gyros which have to be positioned in such a way as to define a 3-dimensional coordinate system, and 3 accelerometers mounted on 3 orthogonal axes. So we have the 3 accelerations in 3 Cartesian axes and 3 rotations around those Cartesian axes. The principle of navigation by inertial navigation system is fairly simple. If we have a precise knowledge of the initial position and attitude of the vehicle at any time, single and double integration of the linear acceleration give the velocity and position of the vehicle, while the attitude is obtained by a single integration of the rotational rates from the gyro measurements. However, what we have obviously will be random errors as well as unknown constant or nearly constant errors. There are drift rates and biases, which obviously will make the navigation problem very much more complex. There are 2 types of inertial navigation systems. They can be gimbaled or strapped down. In a gimbaled system or platform system, we have a stabilized physical platform maintained through a servo system on which the accelerometers and gyros are mounted, and thus they are isolated from the rotations of the vehicle. This not only reduces the requirements on the inertial sensor, but simplifies the navigation computations, because the attitude of the platform with respect to the navigation reference is preserved. However, what we have is a stabilization problem for the platform that makes the gimbaled system more complicated. It's more costly and overall less reliable than a strap-down system. In the strap-down system, there is no stabilized platform. The gyros and accelerometer are fixed, strapped down to the vehicle body directly, and the required reference frame is maintained mathematically by the navigation computer. As the platform moves and rotates, we have matrices that describe the translation and the rotation, and in general, such step-down systems are less accurate than gimbal systems. They are employed, however, because one can obtain with laser and optical gyros and do all the computations these days very easily. So overall, step-down systems are preferred these days. Just a few more words about models for inertial navigation systems. The state of a state estimator model for inertial navigation system is usually chosen consisting of error components, position error, velocity error, and attitude errors of the vehicle. In this sense, the state estimator really acts like a complementary filter because its output is used to correct errors in the output of the inertial navigation system. So the best estimate is the output plus the estimate of the errors. So the output of the inertial navigation system is corrected. An alternative formulation would be to use the full state in terms of position, velocity, and attitude, which requires, it turns out, a much higher sampling rate, and therefore the error state formulation has an advantage that any filter failure will not lead to the breakdown of the entire system because one has the raw outputs. So if it breaks down, there is no improvement. Otherwise, there is an improved accuracy.